Hey friends, hope you're doing fine. Today I'd like to share with you a private project which I was working on, which deals with transfer learning in keras, so in TensorFlow. So what do I do here? Well, at first you can see that I use Google Colab for that, because personally I do not have an NVIDIA GPU, so I can't train my model on CUDA, which is a shame. That is why I need to use Google Colab for that. But it's great that Google provides this free Google Colab that we can train our machine learning models. Even though there's also a pro version of Colab, which probably gives much more options and better resources. But anyway, let's get started. What did I do here? So what I did was I first imported my dependencies, so my libraries, which is NumPy, pandas, matplotlib for plotting, TensorFlow datasets as our source for the training data, and TensorFlow as TF, which is simply the basic TensorFlow. And then I used the cats versus dogs dataset, which again is provided by TensorFlow, so by Google directly, so you can use this as well if you want to follow along. Then I splitted the data here into training, validation, and testing. So basically a split for the training data itself, so I have more data and can also evaluate on my test dataset. Then just to plot and to see what's inside, I can use here my matplotlib library. So I simply looped through here the first 9 images and just take a look at what those images look like. And as you can see, I have here various dogs or cats, while the dogs are labeled as class number 1 and the cats here are class number 0. What's important here is that those images have not the same size, as you can clearly see. So in order to train them and use this as our training data, we need to first convert this so they all have the same size. This is compulsory here for the network. So and that's what I did here. So basically you can see here I specified, okay, all the images should have a size of 150 and 150. So height and length, or height and width actually. And then I mapped this specific, in this case, function. It's simply a lambda function. So I'm using tf.image.resize, which allows us to resize those images, which are the axes here, to the size. And then we also return this as a tuple. That's what we do here for training, validation, and testing datasets. After that, next we need to first use some kind of batch size. So in order to get or to each training step not only on one image, but on several images at the same time. And that's why we specified here a batch size, and 32 was here the number of choice. It's often a number which is divided by 8 or divisible by 8. That's just an additional information here. You can also try out different batches if you want, but 32 is probably a good size. Then I also have here a few additional things, which means, for instance, using .cache. .cache allows us to speed up the training. So that's why I'm using this cache. Then I am using the .batch method here, which allows us to then batch our data into these 32 batch sizes. So that simply the image, or let's say a TensorFlow, then will take 32 images at the same time for each batch. So that's why we specified the size here. And the final one is this prefetch method, which allows us to use tf.data.autotune. This is also, again, some kind of performance optimization in TensorFlow, which allows here to make or to use the network as efficient as possible. So there's nothing to specify here for us. The network itself figures that out. And then I simply printed here what the data looks like now after it ran through this batch optimization here. So you can see we got 32 images with a size of 150, 150, and also 3 color channels. So because those images here, as we can clearly see, are not black-white, they are simply RGB colors, right? So red, green, blue. That's why we have a color channel of 3 in here. And then I simply imported here the libraries. So I'm using here keras from TensorFlow. I also imported the layers, and let me reconnect here. Okay, imported the layers, and also I imported here the exception model, because this is all about transfer learning. Transfer learning is often used because it's really efficient. It allows us to use already pre-trained networks for our own cause. And that's what I want to do here, just to reduce my training time. And then I added here an additional layer, which is this data augmentation. An augmentation layer can help to, create new images, because oftentimes in deep learning, we have the issue that we do not have enough training data. Simply, we need lots of data for training neural networks, and maybe we don't have the data. We have not collected so much data. And this is where data augmentation comes into play, because it allows us to create, well, let's say, superficial or additional data by simply flipping images or by simply rotating them a little bit. By these options, we can create additional images. And that's what happens here in this layer. And then I simply use the exception model. I also said I want to have pre-trained weights from ImageNet, but I do not want to include the top, because I only want to use, well, most of the exception model, so as a pre-trained model, but the top layers I want to train myself for my task. And that's why I say I use it. I do not include the top, and I also set all the weights in the base model as false for training, so they should not be trained. And then here we define actually the model. So we say an input layer, which has the shape exactly of the images. So the layer expects images in this specific shape, which is exactly what we specified up here when we said this is the size we want to have. And then we use data augmentation as another layer for the images. We use our base model, and then on top we say global average pooling, and then we can add an additional dropout layer, which is normally for avoid overfitting of the network. And then we use a dense layer here with one node, because we have either a 1 or 0. It's a binary classification problem. Either it's a cat or it's a dog. And then we simply create the model here with this here and store it in this model variable. And then I print the summary. So the model gets downloaded here, and so the pre-trained model, I mean, and then we have here a little overview, a summary of the model. And that's what I meant here. As you can see, in total, we have over 20 million parameters, and training those ourselves would take a lot of time. But you can also see that the trainable parameters here are only 2000, more or less, 2050. And the reason is that these, all the weights inside exception are frozen. So we keep them, we do not train them. Instead, we only train those last layers here, those nodes in here. So that's why this actually speeds up the training time a lot. And then here we compile the model. So we say, what is the loss? It's a binary cross entropy. We need to specify from logis true, because in the final dense layer here is specified in this way, and we do not have here a sigmoid function. And then we use an optimizer here and also specify what are the metrics. In this case, it's accuracy. And then we simply specify the epochs, and then we start the training with model.fit. We specify also a validation data set, so the model has then also the chance to validate its results against this validation data. And then I ran through the epochs, and it started with here, as you can see, 56 accuracy, 58, and so on, and then it starts training. And in my case, I only ran it for 10 epochs, so not too long, because I did not want to wait too long. But you can clearly see that the accuracy gets better, but obviously it's not perfect, because it's only 61%, so obviously there are a few things to do here. So either we could adjust the model itself, so the structure, adding more layers for instance, or do a little bit more data augmentation, or we can of course also change maybe the hyperparameters, like what kind of optimizer we use, for instance, and other things, right? So a lot of things to tweak, to optimize here, but this was just really to show you how transfer learning can work in practice. And finally, of course, I also checked on the test data quickly with model.evaluate, and you can also see that here the accuracy is more or less the same as for the training data. So, of course, this model is not perfect, and there's lots of room for improvement, but this will just show you how you can use transfer learning in keras, also here in Colab. You can follow this video along, because all the resources and datasets can be downloaded, and you can do exactly as here, and then you can also try out different things to optimize the accuracy. And if you do so, please write this in the comments and tell me what you did and what kind of success you achieved, right? So that's it for this little video. So hopefully that was interesting to you. If so, please give a like to the video, and also please subscribe to the channel. It means a lot, so thank you very much. Then take care, and hopefully see you in the next video. Until then, best guys.